welcoming everybody also.
So this is live, perfect. So welcome everybody. So this is the first session of 3 on a set of talks on fundamental physics. And kicking it off for us this afternoon is Kotaro Moriyama from Goethe University, who will be talking to us about future prospects for constraining black hole spacetime. So with that said, over to you, Kotaro. Thank you.
Thank you so much for your introduction. So today, I would like to talk about future prospects related to the detection of the jet dynamics, especially for M87 ngEHT observation. So previously, from 2019, we successfully detected the first imaging property of M87 with Stokes I, and 2021, we obtained the polarization image and constraints, great constraints for GRMHD models, which prefers matte and positive spin GRMHD models. And in parallel to this kind of great result, Stokes I, based on the Stokes I imaging result, some theoretical work predicts tests a deviation of the Kerr metric, such as based on the post-Newtonian process, and also considering the charge components. And the near future event is based on the 2022 and ngEHT observation, which enable us to obtain the great quality of the image results, not only for the these kind of photon ring component, but also extended jet component. So which is based on the latest analysis from Andrew Shell, and we can if we use ngEHT and 2020 UV coverage, we can extract the external jet components. In addition to these kind of expected updates, it is also expected that a long time monitoring for the EHT observation. So which takes about 30 to 100 days, and which enable us to obtain the jet dynamics of M87. So these kind of expected and interesting future events, we would like to talk about the following questions. So what is can we constrain the black hole parameters, such as the black hole spin, inclination angle, and the magnetic field, by especially focusing on the dynamical property of jet in the vicinity of the black hole. So to answer this kind of near future question, we use the 3-dimensional GRMHD model, which will reproduce a continuous spectrum of the M87 observation. So based with the various black hole spin case, we obtained the corresponding best fit GRMHD model by introducing the non-thermal kappa model, and by using these kind of GRMHD models, we investigated the main dynamics and the dependency to the black hole parameters. So these five movie is representative GRMHD models. What we would like to focus this presentation, and the previous result by Alejandro shows that a stable and well consistent jet components can be seen in the highly and relatively high positive spin case. These based on these kind of left two figures, and the middle and right figures shows the non-spin black hole case and negative black hole case. And the non-spin black hole case, we do not see the large jet components, but we would like to confirm the jet property just in case. And the right component, right movies shows a negative spin case, and we can see that there is a relatively large jet components, but this kind of feature is unstable compared with a positive spin case. So in order to compare with this kind of different spin GRMHD model, we would like to investigate what kind of dynamics constraints the black hole parameters. So there is a three typical time variability we can easily pick up from the near future EHT observation. So first one is the light curve variability. But if we compare with the five typical geometry model, we cannot see the main space-time dependence into the light curve information. For example, if we check the mean and the standard deviation of the light curve, these tendencies quite similar each other. So light curve, instead of focusing on the light curve component, we especially focus on the structural variability, such as the each pixel light intensity variability. So if we take the standard deviation at each pixel and divide with its mean values, we can see these kind of variability characteristic for each image pixel. And in addition to this pixel-based variability, we can sometimes see the clear wave propagation. This is a typical case with highly positive spin case. But if we focus on the right top movies, we can see systematic and radial wave propagation can be seen in the positive X direction. And if we focus on the radial intensity distribution, we can exactly see the variable and wave propagation each other. So we would like to focus on these two spatial variability and check each other. So top panel shows the standard deviation over mean values coming from the five different geometry movie, and the bottom panel shows mean images for different spin case. So if we compare with the positive and the negative spin case, we can see that the variability tendency is large at the negative spin compared with positive spin. This tendency mainly comes from the stability of the jet component. And if we focus on the positive spin case, due to the stable existence of the jet component, the corresponding standard deviation is relatively smaller than that of the negative spin case, which provides an unstable jet component. So this is one of the good indicators for the distinguishing each geometry models. And if we calculate the mean value of the standard over mean intensity for these kind of top images, we can see the clear feature each other. So bottom panel shows this mean standard over mean values, and if we focus on the positive spin case, the corresponding value is relatively small, but negative spin case produce a large and high variable variability magnitude. And if we focus on the spin dependency of these kind of great dynamics, we can see the clear spin dependency. So here we fix the inclination angle, but even for the case, we can see the spin dependency, and which is one of the good indicator for constraining the black hole parameter. And if we focus on the high spin case, 0.5 and 0.94, which is most preferable geometry model, but we cannot distinguish with each other based on only for the this kind of variable magnitude. So let's focus on the radial wave propagation components. So in order to estimate the velocity of the radial wave component, we remove the main jet component and extracts the main wave propagation components. So in order to pick up the radial wave propagation, we compare with the neighborhood intensity image and take a residual of each other. Based on this case, we obtain the time development of this kind of fluctuation per each pixel and takes to obtain the radial distribution to the each azimuthal angle. After get the radial, this kind of radial distribution, we take the nx score between each neighborhood radial profile and estimate the radial velocity. In this process, we try to extract the corresponding radial jet velocity from the complex jet components. So this is a simple example. If we focus on this kind of simple radial and azimuthal jet propagation, we can successfully extract the ground truth velocity each other. So horizontal lines shows the ground truth values, and we can see that each kind of radial and azimuthal geometrical model shows a great estimates for the dynamical velocity, radial velocity. And this is the estimate of the geometry models. And if we focus on the high black hole spin case, which shows quite a clear systematic radial velocity, we can see the non-zero velocity component. So if we focus on the left panel, the blue histogram shows the apparent jet velocity component without considering the, for example, superluminal motion. But if we adjust the velocity by using the inclination angle, we can obtain the true ground truth velocity estimate coming from the ground truth snapshot movies. So this is one of the geometry velocity estimate. And in order to check the original geometry model, we can compare with the estimated velocity shown in the red histogram and the geometry velocity component with weighting the emissivity, corresponding emissivity shown in the blue component. So each geometry ground truth velocity and the estimated velocity consistent with each other if we see the middle panel. And if we focus on the spin dependency of the estimated radial velocity, there is also have a good, clear black hole spin dependency by fixing the inclination angle. And if we compare with a negative and positive spin case, we cannot distinguish each other. But if we focus on the relatively large spin and high spin case, we can distinguish between each other based by calculating the radial jet velocity. In this way, by focusing on the variable magnitude and radial velocity component, at least we can successfully distinguish with each geometry model whose continuum spectral is consistent with M87. So this is based on the ground truth movies, and if we perform the synthetic image reconstruction with ngEHT UV coverage, what we can see for these two dynamic properties. So in this example, as the first step, I do not include the systematic noise and the gain perturbation and the D-term leakage. But this is one of the good exercise for checking if we can pick up the dynamics of the jet component. So here is based on the same similar figure with reconstructed in movies. So if we focus on the radial velocity, we can again see the clear black hole spin dependency. And if we focus on the variability magnitude per each pixel, we can also see the similar tendency between with the ground by using the ground truth movies. So this kind of reconstruction exactly shows the detection of the extended jet component, but we can see the some Brophy-like feature coming from the noise artifact of reconstruction, and it sometimes prevents us to estimate the velocity and the variability magnitude. But even for this case, these kind of simple dynamics help us to distinguished with the GRMHD models. So this is a summary. By using the 5 typical GRMHD model whose continuum spectrum is consistent with M87 case, we can distinguish with 5 GRMHD models by especially focusing on its dynamics of the jet components. And the next step is more large GRMHD survey with different kind of kappa model and other geometry parameters, and checks the consistency of the inclination dependency, and also need to consider the twist jet properties and tilted disk components, but which will require further detection of the for example, azimuthal velocity component and so on. And we also thinking about the deviation from curve black hole spacetime, which will be shown in the next these breakout sessions, and also a more comprehensive method to directly estimate the radial and azimuthal velocity by using the machine learning. So that's all. Thank you so much.
Thank you very much, Kotaro. So we have time for a couple of questions. Any questions? Okay, I'll see a question here.
Hi, Kotaro. Thanks for a really nice talk. You were showing in one of your previous slides, much earlier, the velocity. Yeah, that one. Yeah, I didn't fully understand what the center plot is. Could you just explain what you are plotting there in the middle?
Sorry?
Yeah, the middle plot.
This one?
This center, yeah, that one.
So this is a radial velocity with G equals C. It's 1 unit. Sorry, probably I.
So I didn't understand what you meant by the estimate. What is the red curve there? The red estimate.
So did it run?
What is that?
Yeah, he said he didn't find
Is
Nah,
if we check different graphs, we can see. And also, if we focus on non-spin case, the radial velocity is quite small because there is no but if we magnitude of the black hole spin, the jet
but I think it's the order which is not the same.
from the inhomogeneous structure.
Any question? Well, I'm gonna ask I'll ask a quick question. So a lot of this is based on current motion with the time delay effects, right? Finite speed, the speed of light. Fast light, or as the things move away from the source, the arrival time delays will be more significant. Perhaps some inferences of fast light, not slow light.
Fast light or slow light. This is the fast light approximation. So I'm using that.
It should exist.
Fast light.
What is Can you show me the error?
He said it cannot find, but it is.
Because the first scale is 100.
Then you put where do you place the Python script?
10,000.
But that's the thing.
No, where do you place it? Just because yes.
In Python script.
But do you have this CSV file just inside Python scripts?
No, that is come back. So like if I'm in.
Okay.
Basically, I will here
Okay.
and here Python script. I say come back, and then
Okay.
go to CSV file, blah blah blah.
Okay.
Blah.
Okay.
So he should find it.
While we're setting up,
It seems like he doesn't know.
who will be talking to us shortly.